Welcome everyone to Circuit Lab and Machines Q&A session number 2 for the 2019-2020 season. Welcome everybody. I hope you got your questions ready. The other thing I wanted to remind everyone is that this is not officially by the national office for Science Olympiad. This is just offered to help all teams that might be out there. However, if anyone has any questions or needs anything, feel free to write questions in the live chat as we go along. I see we have 4 people on. Are there any questions before we begin? Okay, I'll type that in here. Okay, very good. I'm glad to see you're back. So you'll notice last week we talked about how to make a potato battery. We also talked about how to make lever measurements. I verified on the national website. They have all the latest sets of slides and such. So before we go any further, I want to show you how to find things on the national website. So what I've done over here, and hopefully the lighting will be better today, is that I have set up my computer here to sort of show you what the national website looks like. Okay. What you'll notice here is that this is what Circuit Lab looks like. You'll notice it's soinc.org/circuit-lab-B or C. You'll notice it has all the resources here. So there's a problem-solving techniques learning CD. There's a test packet, which has the test from the 2019 National Tournament. There is a Circuit Lab kit from Ward Scientific that you can link to here and purchase that. You've got example graphs and diagrams for physics events. You've got the YouTube Science Olympiad TV page, and you've got tryengineering.org, a site powered by IEEE with a page for Circuit Lab resources. You'll also notice as we go down here, we have the 15 sets of slides I was talking about, everything from introduction, static electricity, kitchen batteries, more advanced series and parallel circuits, magnets, electric charge, electromagnets, motors, and sample competition, multiple sources, Kirchhoff's voltage and current laws, specialty devices, LED diodes and operational amplifiers, RC circuits, which is not necessarily needed, but I left it in because it was part of something for last year, PN junctions, and digital logic. So if you clicked on any of these, like I click on digital logic, and you'll see it's opening down here. And I say, okay, let's open it. This one comes up in PowerPoint. And you actually get to see all of the slides for teaching everything for digital logic. And of course, this is only for Division C. We also have the homework generator here and a thing on how to use breadboards. This breadboard design one is a great one because it really shows how the individual holes in a breadboard are connected and how the ones along the top are all connected for powers. It also has some interesting information. It's got a good thing for resistor color code. I would actually recommend this is something that you may want to think about putting in your binder. And then when we get over here to Circuit Lab, the homework generator, here is what it looks like. So you open it up. The first tab is the material and electrical data sheets. This is all from Wikipedia. Okay, this is not exhaustive, but like you can see like the difference in gallium arsenide versus graphite versus mercury as far as the conductivities. The other thing is that it's got the relative permittivities, epsilon, in case you were ever trying to figure out the capacitance or dielectric properties for electric fields. And then since we got permittivities, we got permeabilities. okay, for magnetic. And you'll notice virtually everything that's non-magnetic, if you will, is around 1, okay? Whereas including copper, and so anything you see around 1 is not going to have very much, if any, type of magnetic effect. And then, but you'll see if you get in here, anything with iron in it, especially, or nickel or what have you, is going to have very high permeabilities. Okay. Here is level 1 of simple circuits. So what you see is you have a battery with 3 resistors in series, and it gives you a random setting for the resistances and the voltages. And it wants you to calculate R equivalent, what's I1, what's I2, what's I3, what's the voltage of the resistor 1, voltage of resistor 2, voltage of resistor 2, and what's the power of each, and what's the power total. And of course, since it's a series circuit, first thing you're going to tell me is that I1 equal I2 equal I3, and that's right. That's why this is level 1. The other thing that you'll probably notice is that every time I hit F9 to refresh, it gives me a new set of numbers, so I can keep printing this page out until I get good at it, okay? The R equivalent is just going to be, since they're in series, is just adding them up together, so that's 60 plus 60 plus 60, that's 180. And if I come down here at the bottom, I've got the answers, and it's 180 ohms, and you'll notice the amperage is always the same. The voltages vary. You'll notice that when the resistance and the current is the same, the power is the same, okay? And that the power of each of these added up together gives you the power total. And so that's level 1. And so once you get really good at level 1, you go over here to level 1 magnetism, and now you can figure out if you have current going into this coil and it's going this way, that this is the north, this is the south, and it acts as a very nice magnet. And I notice here I've got a north and south, and I rotate it, and it comes out of the north and goes around to the south. Make sure you put the arrows. In this one, it goes from north to south, and so the arrows mainly go that way. And in this one, we've got a curve, and so you got a loop of magnetic field around it going this way. And in this particular case, I follow it around, and this side of the loop is north and this side of the loop is south. Okay. And what you'll notice about this one is that if I hit F9, every now and then it switches the polarity. So it's not always the same, but it gets you used to drawing magnetic field lines. Then here we have a simple parallel circuit where we just have 2 resistors in parallel. And when I'm looking at these parallel circuits, you know, the key thing I want you to notice here is that the voltage is the same across each resistor. So now that's going to be the same, but the current's going to be different. And that these 2 currents are going to equal to that current, and these 2 currents will equal to that current. Okay. The other thing that you should also notice is that when you have equal resistance, you put these 2 in parallel, that R equivalent is 70 divided by 2, so that'll be 35. I know this one will be less than the smallest number, so this will be less than 10. This will be less than 30. So I come down here, and it's 35, it's 24, and it's 9. So all those numbers make sense. We keep going up different levels, if you will, and you'll notice they progressively get harder, and then they get harder, and then they get much harder. Then we start putting multiple sources in there, combination circuits, how to do switch problem, how to do resistor problems. And so here, every time I hit F9, it creates a whole new set of resistor problems for me. And so this will help you with your resistor identification. And then below here, it also says, hey, if you've got 8 2 kilo ohm resistors, how do you make it into 16 kilo ohms? Well, I just put all 8 in series. Okay. And then it asks if you got 7 8 kilo ohm resistors, how do you make it 1.14? And if you have 8 9 kilo ohm resistors, how do you make that? And so that's more advanced, and you'll learn how to do those designs. You got Wheatstone bridge problems then. You've got dependent source problems. You've got superposition problems, Norton and Thevenin problems. We also have a data sheet here on LEDs, but keep in mind, sometimes they'll have different numbers used. And then we've also got some simple diode problems. So all in all, about 17 levels or 17 tabs for Circuit Lab. Are there any questions on that on the national website? Okay. So now let's talk about with machines. And guess what? With machines, we got sort of the same thing. With machines, if I go over here and I look at the machines webpage, again, we have lots of internet links. We've got Simple and Compound Machines DVD. We've got the chemistry physics CD. We've got the example graphs. We've got 8 lessons that I created for simple machines, which basically is an introduction to machines, explaining what force, friction, torque, and levers are, pulleys, wheel and axle, wedges, incline planes, screws, and then how to build a lever. You'll also notice I also created a homework generator for machines as well. Hold on a second. Here we go. And you'll notice here, level 1. Hold on a second. You got level 1 levers, which are very simple. You'll have class 1 levers, class 2 levers, class 3 levers, etc. Okay. Well, actually, it's got 2 class 1 levers. Then the more advanced levers, and what you'll notice here is that the answers are not always as easy. Okay. But this is to get you used to the concept of trying to figure out whether or not it should be more or less, the IMA should be more or less than 1, and whether the effort or load which one should be larger and which one should be smaller. Level 3 levers are even more complex. And what we start doing there for these, hold on a second, let's view normal. You'll notice here is sometimes I'm asking you, hey, what should that distance be? Sometimes I'll ask you, what should the other distance be? What should the IMA be for that load? And the reason why you do it this way is that you never know what they're going to provide you and then what they're going to ask you for. Okay. We've got level 1 pulley problems here where we actually look at pulleys. Okay. And you've got a very simple pulley here. You've got a simple block and tackle here. You've got a more complex pulley here. Okay, now we're starting to get into a double tackle here, a gin tackle here, and a 3-fold purchase. Okay, and you have to learn how to do those. And then for level 2 pulley problems, what you'll notice here is that now we're talking about belt pulleys. Okay, where the difference in diameters of the various pulleys will give you different forces at the edge, and will give you different torques. And so you'll see I'll be asking about the torque and the speed and the gear ratio, etc. Then we've got level 3 problems. And now I'm not only asking about the differences in loads, I'm asking you about the effort distance. Okay. And you'll also notice is that some of these are perfectly efficient. Okay. And some of these are not. So it actually gets to be much more complex. We've got simple wheel and axle problems here, where you have to look at the ratios of the radius. Then we've got wedge problems. And what you find out with wedge problems is that wedge problems are usually the easiest of all the problems. And honestly, you're just really looking at the length versus the thickness back here. And the sharper it is, the better it cuts, but the less it separates. And the more broad it is, the better it separates, but the less it cuts. So you get less of an IMA. Then we've got inclined plane problems. And then we've got inclined plane problems now where I'm going to ask you different questions. Okay. And so that's all the things that I have for machines as well. Will it grade you after you fill out the homework? No, it won't. You'll have to grade yourself. But the good news is the answers are always on the bottom. No, it won't. But the answers are on the bottom. And my number one rule is don't consider it good unless you get 100% on each sheet. So in other words, I generally stay with like level 1 until I get 100%. And after I get 100% a few times in a row, then I go to level 2. After I get 100% a few times in a row, I go to level 3. Then if I'm having some problems, I might go back and do a couple extra sheets. Okay, any other questions? Okay, so with that, and hopefully the lighting has been better. What I've done here is that I have created a very simple setup where I have a 9-volt garden battery or a garden light. It's a DC light. I've got a whole bunch of leads here. Okay. I've got my handy dandy multimeter. I've got some switches and some batteries. Okay. Now, hopefully this multimeter will be fairly easy to read. This is what they call a bench multimeter because it sits on the bench. The other type of multimeter, the one that I showed you previously, was the type you normally get at Harbor Freight, if you will. And this is just a normal type of multimeter where I could turn it on here and you can read it as well. But we're going to be using the bench one because it's just a little bit easier for me so I've got 2 free hands, but it works exactly the same. So what you'll notice is the first thing I almost always do with my multimeters is I put these little leads on the ends of them to make it easier because clips are always easier for me to work with. Okay. And you'll notice here I'm measuring voltage and it gives a lot of crazy numbers, but when I put them together, it gives me 0 millivolts. Okay. Now, that's a good sign. The other thing is I can measure voltage on DC. I can measure it for my batteries. So if I measure my battery, you will notice it's minus 83.5. Okay. And that makes sense because I put the negative terminal on the positive terminal and the positive terminal on the negative terminal. If I measure it the other way and put the positive on the positive and the negative on the negative, I get plus 8.35. Makes sense. Now you'll notice I generally only measure voltages. I like to measure voltages. Occasionally I'll measure resistance. I never measure current. So that one's 8.35. So that's a battery that's just about dead. Okay, when you get about a half a volt or less, that's usually when they start having problems. So now I got another 9-volt battery here. Just trying to make this where you can actually see it. Oops. Here we go. And so now I measure it. And I get 8.32. Also pretty low. Okay. Now, I also happen to have these switches. And these particular switches are what we call double pole, double throw switches. Okay. And these are used quite a bit with wiring a 3-way switch, but you can also use it as a single pole, single throw switch. What you'll notice is one side here, these are your A and B outputs. So when I flip this switch here, it doesn't have it on and off. I'm basically internally going from this black, if you imagine this black node here, this black screw here being one node, I can switch where it's connected to here or it's connected to here. Now, if I just set it up such that the black node, if you will, is where my power comes in at. Okay. So I hook it up like that. And I only use half of it. Okay. So I'm hooking it into my battery here. And I take this half, and I'm only going to use half of it here. And Now, I can now hook it into my light. Okay. And then this part here, I can now hook into. And what will happen here is that now, if I flip the switch, the light turns on. If I flip the switch, the light turns off. So I'm actually treating this switch, even though it's a double pole, since I'm not using the other pole, it's like a single pole, single throw switch. Okay. Now, I can also measure voltages again. If I measure here and here, I should get the same battery voltage I got before, which was 8.04. Wow, we really started to drain that battery. And if I measure from here to here, I notice it's still about 8.04, 8.05. Okay. What that tells me is that if I have the same voltage here as I have at my battery source, that's usually an indication that that's where my break is. So what this tells me is that the reason why this light isn't on is because this switch is not operating. Because if I measure the voltage, let's say from here and from here, it's 44 millivolts or virtually none. So what that tells me is there is no voltage being lost from here through this light through there. So what that tells me is that there's no current going through there. And more importantly, there's no voltage difference. The voltage difference is here. And now when I flip this switch, that light's going to turn on. See? And now when I measure the voltage at the switch, it's virtually zero, which makes perfect sense because all my voltage now is between here and here. When I compare it here, I get 2.6. And you say, why did it drop all the way down from 9 volts to 2.6? And that's because this thing is drawing so much current, it's draining my batteries really, really fast. Okay. And so what that tells me is I probably, if I was going to make this a long-term circuit, I'm going to need a different power source, or I'm going to need to put something in series to just keep it from draining my battery. And that is how you use a voltmeter to troubleshoot a circuit. Are there any questions? Going once, going twice. Okay. All right. Last thing we're going to do is a machines thing. Okay. And so the machines thing that I'd like to do is that we now have everybody's favorite lever here, the class 1 lever. Okay, this is the same one we had last week. You notice we got a notch here on the short side. We've got all our markings on the long side. But guess what? My counterweight fell off. Now you'll notice my counterweight is just simply put a large bolt with a whole bunch of large washers and a big nut on the end. Okay? But if I take about it in the middle like this, and I put it right here, I can probably get it balanced. And then I tighten it up just by hand. Notice I'm not over tightening it. And I try to get it to where it's nice and balanced. All right, I need to move it back a little bit. And by the way, a good balanced one tends to be a little less forgiving. All right, now I've got my masses with the loops, And you'll notice the loop. A golf ball fits through the loop. So that's how I know these loops are nice and legal. Okay. And again, I want to make measurements. So we're going to go back a little bit. Okay. And what you'll notice is here, I hold these in my hands. I go, this one's a little heavier. So I put it on this side. Put this one on this side. And then I just slowly move this one over until it's nice and balanced. That's about balanced there. And you'll notice I don't spend a lot of time. It comes out exactly at about 1.5. Well, guess what? I measured these before, and this is 300 grams. And I measured this before, and this is 200 grams. So 1.5 was the right answer. Now you'll notice, because it's a really lossless lever, if I have wind on it, like I do here, I've got the ceiling fan going, or if I let it get out of balance too much, it'll flip up or it'll flip down. And so again, you've got to be careful when you have a really nice lossy lever. Okay. All right. The question, we got a couple of questions. One is, how would adding a resistor allow you to use the same battery? Well, real simple. If I put in a resistor, okay, it means that the resistance, and you didn't see me measure the resistance, but the resistance for that particular light bulb is about 0.9 ohms, so about 1 ohm, okay? And so what I can do is, let's say I put in a resistor that's like 2 ohms, okay? What will end up happening is, or let's say I put in a resistor that's like 1,000 ohms. Put a resistor that's 1,000 ohms, most of the current is going to be really low, but also most of the voltage is going to go into the resistor. Okay. And that won't drain the battery near as fast. Problem is, the ratio needs to be such that I can really make those light bulbs work. And actually, I don't think they're 9 volt bulbs. I think they're more like 3 volts. So I'd probably want to put a 2 ohm resistor, and then that way I'd have 6 ohms or 6 volts going into the resistor and 3 volts going into the light bulb, but I'm only drawing 1/3 the current. Is that the type of hands-on task at Science Olympiad? Absolutely. And so you need to be able to look at the switch, figure out what type of switch it is, whether it's a single pole, single throw, which is the most common type on-off switch, whether it's like that one, a double pole, double throw, etc. And then you need to know how to wire up simple lighting circuits. So know how to do lighting circuits, know how to diagram them. That's another very positive hands-on activity. So with that one, the hands-on activity might have been to set up a light bulb that works, but they would also be to measure all the voltages and figure out how to measure the resistance of the light bulb and then draw the diagram. I always ask to draw the diagram. And sometimes I'll say, draw the diagram of the lighting in the house for a light and a fan. Okay. You might have 2 separate switches operating each ones. All right. Any other questions? Okay. So just keep in mind, this is the last one until December. We will not be meeting next Saturday or Sunday, and we will not be meeting the following Sunday on either side of Thanksgiving. Okay. But that first Sunday in December, which I do believe is December 8th, we'll start it back up. Tell your friends to subscribe to the channel. Type any questions you have in below. And I will see everybody in December, and good luck and keep studying. Unless there's another question. Okay. Thanks, everyone.